But guess what? It's pure convention anyway. I can absorb any z you want. You give me a z of 3, I have a z of 5. I couldn't tell the difference because all it is, ultimately, I've said it in this language, you can just redefine it away. It's gone. You say, well, it's got to show up somewhere. And yes, it shows up in the strength of the source. And the source you buy off the table somewhere, I mean, buy off the shelf somewhere, and it tells you it's this efficient. Okay? So this, I claim, is pure convention. Okay? So we can redefine this away by going from phi to phi prime u. And the Pauli-Villars theory, that's a certain redefinition by a certain theory. In the true theory of everything, it's a different transformation. But it's gone. It's pure convention. Now you say, okay, I'm willing to concede that much. But this is not pure convention. It's clearly, I can't field redefine this away. It's sitting there. And it is this messy expression. And again, this expression is surely wrong. This is an expression calculated in a fake theory, Pauli-Villars ultraviolet theory. And then somewhere, there is the true theory of everything, which gives you a different m squared for normalized. How am I to get my hands on that? I need to know the true thing if I'm going to go compare with experiment. And so we're going to go through this now, not next month. We're going to go through this now. I'm going to say it once, and then we're going to go through it a little more systematically again. Okay, so I'm going to say it once the easy way. You don't have to go and calculate this. We have calculated it. Here's the expression. I've calculated it in crazy theory of Pauli-Villars. But it's just holding a place for the true calculation. And the reason I don't have to calculate it is because I can measure it. If this is a quantity that's measurable, because you can plug it into interesting processes, you can measure all these things, you can measure the S matrix, and you can fit what this is. Okay? If you can do that, this will be one of the fit parameters. Okay? So, instead of saying this is an output of a calculation where you give me a mass parameter, little m squared, which I can't measure, which is unphysical. I can't see what that is. The interactions dress this m squared with all this other junk and gives it to me in this box. And all I can do in an experiment is go and measure this. Okay? Or extract it fit to experiments. But then the right way to think is, let me measure this as an input. I take it from experiment. Because once I've taken it from experiment, I've got the entire function. Okay? See, this is actually a function of p squared. A function is a lot of information. You just have to measure a few numbers. G, go and measure it. At the order we're working, it's just something you can measure from a 2-to-2 scattering process. Right? Just go extract G. You go and measure this, or you fit these processes to experiment and extract this. And once these are inputs, and capital M as well, you've got the entire function of P. Okay? That's the value added of the calculation. So the trick is not to agonize about the fact that this measurable, fittable parameter is a horrendous and probably untrue function as given here. Probably untrue because Pauli-Villars is surely not the theory of the ultraviolet. But instead, there is some true ultraviolet physics that gives you some more complicated version of this formula. But it just sits here. and we just go and measure it. We say, I don't know the ultraviolet theory, but I'll just measure this parameter, and everything, so the right way to say it is these two things are ultraviolet sensitive. So, by which I mean sensitive to new lambda scale physics. All this calculation shows us, by actually going through it all, is that these two quantities are very sensitive to the new lambda scale physics, and I don't know the new lambda scale physics. The Pauli polars is surely not it. But here is a whole function of p squared, and there are only two numbers that I don't know. One number is unphysical, so just throw it out. That's one number I don't know. I mean, fit it to experiment, and you have the entire function. Okay? So the trick is that as input, if you want, in a Gedanken experiment sense, or a real experiment sense, we fit M renormalized M, which at this order is the physical mass of the fermion, this order of work, and G to experiment, and then we can predict the function, the dress propagator, which is a function of p squared, which is a continuous infinity number of numbers, right? A function is a bunch of numbers. That's the value added. And the fact that the structure, that even if we do the true calculation, that it's going to look like this, with just under the hood, the formula here will look different, but that will look like this, I'm going to prove to you. Okay, but I just wanted to say it once. That this fake calculation is sort of standing in for our best guess of the kind of thing that new physics can do. We don't believe every detail, but we don't have to. As long as the structure of the final answer has this form, we will redefine this away so it never occurs on our watch. And then this, we simply fit to a data, and then we have the whole thing, and we have a finite answer. Okay? So our job is to know how to make these moves. Because in the end, you want to calculate that cross-section or something like, or predict something to several decimal places. We are going to have to learn the moves that get us these finite answers, and the art of figuring out who are the inputs. Where do I just sort of measure? There are certain things which are highly sensitive, but I just go and measure them. And the number of things, here is a function of p squared. Most of it is insensitive to the ultraviolet. And there's just a couple of places where you have sensitivity. You measure those sensitive parameters, and then everything else is predicted. Okay, that's the value. There was a question from that. Yeah.
First, I don't know, but I think what we measure is going to be a renormalized mass squared plus real part of the final expressions of there. And is that the physical mass we would measure in the experiment, not just the renormalized mass?
So we're going to talk about, we'll talk in a little more detail, but let me say that right now you could say, look, we already have this discussion. The physical mass is the pole in this propagator. Now, the pole, this is not the pole in this propagator. There's some p squared dependence here, and so I have to do a little work to hunt for the pole in the propagator. This is not the physical mass. It's not the physical mass. However, it at least makes clear that here is a function of p squared which is finite if somebody told me this. Now, the entire function, I could do experiments to scan. Remember, I could do these kinds of experiments where the p, look, in the most general form, I have a source of scalars. So there's a p squared, and the source allows me to tune the p squared. And here's a detector. I can scan in p squared. I don't have to sit on mass shell for this scalar particle. I can scan in p squared. This is just a virtual particle, but it plays a role in this process. And by scanning in p squared, I can actually figure out, oh, there's some piece, I can fit it to this formula. And when I fit it to this formula, that'll be one of the fit parameters. It is not the physical mass. Not yet, okay? Because it's a rough approximation of the physical mass, because this is order g squared, so I couldn't throw it away. But it is not the physical mass in detail, which we'll talk about. But it's more. But this is a more general purpose use than just figuring out the physical mass. If I'm off p squared, if my p squared is not on shell or close to on shell, this is still a useful thing, okay? And that parameter comes in. So there is often a no. Let me say that later.
Second question is,
yeah.
Although renormalized mass is going to be a combination of UV sensitive expressions,
yeah.
But at the end of the day, I will get UV insensitive result for renormalized mass itself. Is that right?
No, we will not get a result. So when the question has the form, will we get a ultraviolet insensitive form for the renormalized mass? The word form means that there would be a formula for the renormalized mass in terms of other quantities, okay? But the whole art of renormalization, the whole science of renormalization is to figure out who are your inputs. You cannot predict without any input. You have to do some input. So what are the inputs and what are the outputs? And if it's a theory, then we hope that the number of inputs is small and the number of outputs is big. Okay, the number of things we can predict is big. So what we're noting here is, if we take this as an input, rather than little m, if we take this as an input, then everything else is just a finite function. As an input, when we think about where did it come from, we might worry that it is a UV sensitive quantity, that I cannot just predict what this is by pure thought. It might be affected by all of these processes, this imagined new physics. But as soon as I take it as the input, I don't get a UV insensitive form, because form means write it in terms of something even more input-y. I have no more input. This is it. I have traded this one rather unphysical thing, which I would have a hard time fitting to, because I could go around fitting this to experiment, but I just wouldn't, I would never trust that my Pauli-Villar's log here is the right answer. But as soon as you tell me, no, this is the form, then this is the input, and we take it as the input, and we throw away any sense of this little m as being relevant. It's merely an intermediate step, okay? And we get this.
So it is UV sensitive form, but it is UV finite.
Yeah, it's a UV insensitive. It's a UV sensitive object.
Right, but it must be UV finite. I mean, it must be finite.
And we assume that whatever UV stuff is up there gives us it's a finite quantity, but it's a finite quantity which is very sensitive to some ultraviolet masses and so on, as represented poorly by lambda. And I say I don't know what those masses are, and I say forget it. I'm just going to take this as I'm going to measure my way out of this problem. Okay, I'll measure this, but having measured one number, you might worry. In fact, there's a real worry. If UV physics could affect this quantity, as this fantasy suggests, if it could affect this quantity, maybe UV sensitivity riddles the entire function of p squared. Okay, how many things can I measure as a way of avoiding calculating them from a more fundamental theory? And the answer is no, it doesn't affect the whole thing. Okay. Now you might say we're doing one case study, and now is that more general or not? And it is more general, and our job is to understand what is the general structure of this work. Okay, it's a really stunning and beautiful realization, but right now we're just.
Can I ask a question, Raman?
Yeah.
So what happens at higher order? If I want to go to higher order, there were UV sensitive parameters.
And so, what
would I do to just connect to the story?
I'll just assert it right now, but then we'll talk. wait a month, right? But what will happen is if you have to work consistently to order g to the fourth, and you always find, in this theory, you'll always find that all the ultraviolet divergences can be subsumed in the same sense that there are ultraviolet divergences which are housed in this secretly. But I just measure it, and then I say I don't care about predicting it, I'll just measure it and take it as input. In the same way, you find that even if you go to higher orders, all the ultraviolet divergences, all of them, are hiding inside a renormalized little m, a renormalized big M, a renormalized G, and that's it. And actually a 5 to the 4th, kind of, a lambda 5 to the 4th that you're forced to throw in, which I'm not talking about in this order. Okay. So basically, and we'll see this, but I'm not just asserting it. Later on, we will see why this is the case. But and so you can go to any number of powers or orders and perturbation theory, and you just have these 1, 2, 3, 4. You have 4 experimental quantities to take as input because they're incredibly sensitive to the true ultraviolet. But they're the only 4 quantities that are incredibly sensitive. And every other function of momentum in the S matrix is finite as a function of those 4 input parameters. That's the beautiful move. Okay.
So since we were working only to order g square,
it
was all right to just use the capital M and the little g and not worry about their renormalization.
Correct. And
but if I wanted to work to order g fourth, then all of them will play out.
They're all coming into each other. So the simplest of simplest cases where the minimal amount of this getting renormalized affects this other, the minimal thing is in the homework, okay, in a certain approximation, which is rigorous, a proper approximation scheme. You can make the fewest moves and you get to play with it yourself. I think there's nothing like drawing a experimental picture starting from things which are riddled with infinities and you think you're dead, right? That if you can do it yourself once, then you feel like, okay, it's not that bad. Okay, so the homework, I think, is designed to be the simplest case of that type. Yeah.
I just have a question. I want to confirm my physical intuition about this term that's the integral over dx and has the extra p squared dependence. This is effectively an approximate self-energy term if we compare this to the original Dress propagator equation. So we had that Dress propagator where it was p squared minus m squared minus the self-energy.
There it is,
And then, so that term is the order g squared of the self-energy.
Yeah, so
after we've done all this renormalization and taken into account that there's new physics somewhere.
That is almost exactly right, and the exact right is sort of staring you in the face in the sense that clearly, if I do this, at least this renormalization of the z, then this old m squared plus this is the renormalized m squared plus this.
Okay, so there's a little mixture potentially.
So it's so one way to say it is even this, and I'll do this later, but let me just say it now to answer the question. I could always put REN here and REN here, and just say I define that to be the definition of sigma renormalized. So then the quick answer to your question is yes, that's exactly what you said is exactly right. Sigma renormal, there's a renormalized sigma, which is absolutely finite, and you're staring at it. There, look, you don't see any infinities whatsoever. Okay, so that's and we'll design that notation. So maybe this is a easy way. So I think I can. I don't want to keep the suspense about, you know, all of this was worked out in this Pauli-Villars theory, which is clearly a kooky theory. And what about the real physics? Like, what's really happening? Okay, so let's ask why the kooky theory, the regulated theory, is still giving the correct structure. I say structure because the formula for m squared renormalized in terms of these antiquated parameters here may be wrong, because that's Pauli-Villars theory, which is nuts. But written in this form, this picture, this formula here, is actually correct. Okay. Even though I did it in a dumb theory. Why? Why the insensitivity to how stupid I am in modeling the ultraviolet? Let's see. I think then I can give you satisfaction. Sleep at night. So let me start with the original sigma Feynman diagram. Okay? Unregulated. We write it out as a set of integrals. It is a meaningless expression. Okay? But this is not, well, this is less meaningless. I'm going to differentiate this expression of sigma as an integral. I'm going to differentiate it with respect to p squared. Okay? And you can sort of look at your old expression for sigma and do this in your head, because it's pretty easy. So let me just write it out. You get minus g squared over 8 pi squared integral dx integral dq squared q squared over so I'm just giving it in that Wick rotated form. Plus, so remember there was a term which was independent of p squared? That's gone, because I differentiated it. So there's just this other term. And when you differentiate it, there was a p squared outside the integral, and that's what I've hit here. Or there was a p squared inside the integral there, and that's what I'm about to write down. And presumably I'm writing it down incorrectly